All right, so we're back with our last few examples. The first one we're going to take a look at, you've seen something similar to it before, but there's a slight difference. So in this example, we have two cars that are moving in a perpendicular fashion from each other. So we've got a north-south highway intersecting with an east-west highway, which you know would create a right angle. And that's intersecting at point P. So I'm going to go ahead and call that point P. So an automobile crosses point P at 10 a.m. and travels east at a constant rate or speed of 20 miles per hour. So I'm going to mark that. At the same instant, another automobile is 2 miles north. So that's important because that means you know that distance starts 2 miles north of P, and it's traveling south at 50 miles per hour. Notice my negative. Find the time at which they are closest, so we're going to be minimizing something to each other and approximate the minimum distance. Okay, so we're basically looking at the shortest distance. So we have this Pythagorean relationship. You probably saw that coming. And so we're hoping to minimize z. So that means we need a relationship on z. So we're going to start with our Pythagorean relationship. And now we need expressions for the sides. This is where it's a little different than related rates, because on this we're working on minimizing, so we don't actually know where they are at a particular time. We're looking to minimize a value given a particular, or finding a particular time. So for this side over here, we know that this side started at 0 length and then started growing 20 miles per hour. So we're going to let this be 20 times t, because every hour it's going to grow another 20. So that side will be 20t. This side started 2 miles long and you're losing 50 miles every hour. So as you can imagine, 2 minus 50t for that side. And then this side will just be stay z. Okay, so over here, let's fill in what we know. X is 20t, y is changing at a distance of 2 minus 50t squared, and then we've got equals z squared. So we don't need to take the derivative here. This is literally the expression for the length. We're not looking at the rate of change of z. So if we wanted to get an expression for this, for z, all we would need to do is take the square root. Now I'll go ahead and expand this out for you. You would have to take the time to do this on your own, but it does come out to this, and then I need to square root both sides because of the fact that it was z squared. Okay, so remember, this is what we're trying to minimize. But to minimize that, we need to look for when the derivative is a 0, right? So remember, we're looking for when z prime of t equals 0. So let's take out our calculator and take a look at what's going on. So let's plug our equation in. So the first thing, I am going to be looking for the derivative, but I'll show you again how to do that in your calculator. So I'm going to be plugging in the square root of that equation. Now I'm using an x instead of a t, but it's fine as long as you have one variable. Okay, so there's that equation. But we want the derivative so we can see when that is 0. So if you remember, I told you could go to math. You can go to this derivative function. You're going to say x because you're doing it with respect to x. You want to do the derivative of the y1, so we go to the variables button. Over to y variables, we choose the first one, and there they are. And then because we want every possible value, so it creates a graph, we're going to put an X right there. So now technically it would graph both. If you only want it to graph the derivative, which technically we do, you can go back up to the top one, unhighlight the equal sign, and it will only graph that second derivative. So now this graph is interesting because it's a very, very skinny, quickly increasing graph. So you're going to see in a minute, there it went. It's very hard to tell where it might be, right? I mean, you could zoom in, but I find it easy. If it's really difficult, I just go to my table and I start looking at these y values. And remember, we're looking for when this derivative is 0. So we're looking for a change in negative to positive. And if I continue to go up here, this stays positive. So that change is happening right here, which is between 0 and 1. So when I go to my second calc to do 0, instead of having to move my cursor left and right, I can literally tell it what to look between. So the left, or the smallest number I want it to look between, is 0, and we said positive 1. You might have to watch that a couple of times, but you can get that. So that looks like my 0 happens at 0.034. So let me write that down. So the time is 0.034 hours, which I could convert to minutes if I wanted to. And then we want to actually plug that back in for z. So a couple of options. What I would probably do is go back and turn on my first graph so that it will also graph. And then I'm going to actually just plug this value in because remember, this is like my x. So then once this is done graphing, I can plug in my value of 0.034 and you'll see, even though we have two graphs on here, you'll see how we can differentiate between the two. So if I go to second calc, I want to plug in this value. So I'm going to choose that first option. And so I'm going to put in 0.034. And so here's my y value. So here's the length of actual z. Now, if you're not sure if you plugged it, if you're looking at it plugged into the right function, it tells you up here. Like this is what you get when you plug it into y1. If you hit down, it'll plug it into the second one. But we don't really care about that. We care about what it is when we plug it in for the original. So 0.734. So the closest they ever become to each other, closest they ever get to each other is 0.734 miles. Okay. All right, last example. You see this one quite a bit because this one deals with um, profits and companies. And so this is a very commonly used relationship for calculus. So they tell you here the owner of an apple orchard estimates that if 25 trees are planted per acre, then each mature tree will yield 700 apples. For each additional tree, the number of apples produced by each tree decreases by 20 per year. How many trees should be planted to obtain the most apples? So we're looking to maximize number of apples, which means we need an expression for the number of apples. So let's start there. Well, we know this. We know that if you have 25 trees, you would produce 700 apples. So if you wanted to, each tree, excuse me, produces 700. So I could take 25 times 700, and that would give me the total number of apples, right? But this we have a fluctuation because what we know, I'm just going to let it be number of apples. I guess I'm going to use a t, so I'll do number of apples given a particular t. You'll see what my t is in a second. Okay, so it says for each additional tree planted. So you started with 25, but you're going to add a tree. So I'm going to let the number of trees I add be my t. That's the fluctuator here. We said that the number of apples produced, which typically would be here in our relationship, decreases by 20. So we would have 700, and then you'd lose 20 for every amount that you change. So in this case, T isn't the number of apples or the number of years. T is the number of added trees, I believe. Yeah. So again, 25 plus how many trees you add for your yield, it's going to be 700 minus 20 per tree that you have added. Okay, so this is giving us our relationship for our apples. We want the most. So again, we want to maximize this, which means we're going to look for when the derivative of this is 0, and specifically when it's 0 when you go from being a positive to a negative. So keep that in mind as we do our equation. Okay, sometimes you can multiply this out and you can factor and find the zero. You can find the derivative and find the zeros and such. So for this particular one, we can try taking a look at what that would look like. So let's see, if we multiplied this all the way out, I get 17,500. And again, I'm just foiling it out, plus 200t minus 20t squared. If I take the derivative of this, I would get 200 minus 40t. So you can see this is going to be real easy to do by hand because some of these you won't be able to use a calculator with. So then for this guy, I can set this equal to 0 and solve. I will have to be careful about the increasing and decreasing, but we can talk about that later. So in this particular one, I end up with 5. Now, the question does say how many trees should be planted to obtain the most apples per year. Well, your answer isn't that a total of 5 trees should be planted. You're going to plant 5 additional trees. So make sure that your final answer here is you should be planting 25 plus 5 or 30 trees. You could also figure out your actual apple yield by plugging 30 back into the equation, but that wasn't part of the question. All right, you've got a nice problem set to be working on. Some are a little more difficult, some are pretty straightforward, so good luck.